Assalamu alaikum, Bismillahirrahmanirrahim. Welcome to lecture number 26, the last week lecture, and also the last slides of the basic mechanical engineering course. Well, in first we just revise our previous slide, then we will move towards to the last numerical of basic mechanical engineering, that is related to HVAC. Anyway, in the previous section, we just learned the basic component of all types of vapor compression cycle component variations, or we can say that formation of the cooling cycle. Like we have studied the air cooled system, we have studied the water cooled system, and even water rejection system as well. As well, in this diagram, all the detailed central air conditioning system can be seen. Like if I draw, this is the air side, this is your room that is ventilated by circulation of air conditioned air with the mixing of fresh air as per requirement, as per ASHRAE law, that is 35 liter per second per person. Anyway, then the air is cooled down either by chilled water, just like this, and the chilled water is circulating by a pump that is also controlled by a valve. And the chilled water circuit, this is the basically the heat exchanger, where uh, the refrigerant is cooling the water, and this is the refrigeration cycle. This is basically refrigeration cycle. The basically there's a condenser, refrigerant cooling the water, and the water is going to the heat exchanger of air handling unit that cool down the air. And lastly, the heat rejection cycle, that is related to the cooling tower. The condenser, this is evaporator that cools down the water, and this is condenser. And the condenser, the refrigerant also not cool down, but the phase change from the gases to liquid. You've seen that after compression, the refrigerant gases in the gases state, but in the condenser it's cooled down, but not the temperature. It changes the phase from gases to liquid here. Okay, in this type of a Sharon tube heat exchanger, we can say. And that the water which is cooling the refrigerant, basically the water which is itself gets heated, but change the phase of the refrigerant from gases to liquid, is then cooled down by this cooling tower, and water circulated by the pump with the control valve. So the main cycle is again the refrigeration cycle, air condition, sorry, not we cannot say that it is a refrigeration cycle, air conditioning cycle, vapor compression cycle. The main is the vapor compression cycle. The air the cooling goes from this side to this side, and the heating is rejection from this side to this side. So basically we have a for loop. If we just I just go to the next slide, this is cooling tower, we already learned. And after that we will start now. So I just want to revise with the physical drawings that I used to write in the whiteboard, and also I used to visit all the students to our mechanical engineering lab, where all the components are available in the physical form, so you have a better understanding. Also I visited all the BME students to backside of our conference room or auditorium. You see that auditorium is a big hall for events like conferences, etc. So behind that we have a chiller system, the commercial size chiller system. And I used to visit that backside of a conference auditorium hall, where the water cool system is running, and it is cooling by the cooling tower. So it is very learning way. But Unfortunately, due to corridor, I cannot show you physically all the system, but still I just tried my best by showing the pictures. And also I'm going to draw and make you little bit understanding of all kind of three system. The first system is very basic system, you already learned in many of the slide. Like we have a compressor, that is a main running system, and the compressor compresses the gas. The gas is going towards the condenser, then it changes the phase from gases to liquid, then it's going to the expansion valve, and then expansion valve to the evaporator. Okay, so basically this is the most simplest cycle. In commercial size central air conditioning, we have two kind of setup. One is air cooled chiller and other one is water cooled chiller. The difference is in the condenser side, where the cooling, normally in the homes you can see that the condenser is cooled down by natural air by blowing the fan, but in the commercial size chiller it is cooled down by cooling tower, or even though if it is not cooled down by tower, so we have to place big fans to reject heat of a condenser to the environment. And again, the refrigerant size can be cooled down directly the air by placing that evaporator in air handling unit, or by cool down air instead of air, cool down water by running the pump, and this water again goes to another heat exchanger which cool down the air, and this air will circulate towards the room that's shown in our previous diagram. So basically this called air cooled chiller system, where the condenser air is cooled down by natural air by blowing the air from the condenser, but the chilled side is transferring towards the water into the water, and the water will cool down the air, which air goes into the our rooms or central chiller, central conference room, etc. Another, just sorry, we go to the next page. Yes, this is the next page. Another system, another composition could be like this. We have a compressor. We have a compressor that is connected with the condenser. This is condenser, and the condenser goes to the expansion valve, and then we have a evaporator, and the evaporator gas again goes into the compressor. So in our central air conditioning system of auditorium, we have a setup like this. We have a condenser side which is cooled down by the water. We have a pump installed over here. The pump is transferring in the condenser shell and tube heat exchanger, and that water goes with the control valve. Control valves control the water that goes into the cooling tower. This is our cooling tower where it's showering. You can see the backside of the conference room, you see that cooling tower, and this by evaporation process the water cools down very rapidly, and this cold water goes again into the condenser, gets heated, and then cooled back down the cooling tower. So but the air side is not cooled by the chill water, it is directly cooled down by refrigerant. We have a refrigerant gases, that is after expansion valve we have a refrigerant gases, and we have a heat exchanger that is confined by main air handling unit, and after air handling unit we have different diffuser, different branches of a air handling unit that goes into the main conference room, and the air is cooled down by this. We have two loops. One is we have two two branches of supply air and also two branches of return air. So this is the loop of return air and this is the loop of supply air. It is not very clear because I just have a touch pen, so I cannot make a very perfect drawings, but for understanding I just draw these drawings. So this kind of a setup is installed in our main auditorium. Yes, but in many offices, in commercial buildings, or in industrial setup, we cannot directly cool down the air by the refrigerant, but we just see the cycle of air cooled chiller system, just like here, that refrigerant gases cool down the water, and chill water goes into the air handling unit that cools down the air. So this kind of many composition of central air condition possible, and you have learned all this type of configuration in previous slides. Now let's move towards the last topic, that is cooling load estimation. This will be the last topic of our HVAC system, and only one numerical we will cover in this section. So the cooling load estimation required to estimate the cooling load, we need to estimate the heating load, that how much heating is producing in the room, offices, or any malls, etc. So the total heat required to be removed from a space in order to bring it at the desired temperature by air conditioning and refrigeration equipment is known as cooling load. The purpose of load estimation is to determine the size of the air conditioning and the refrigeration equipment that has to require to maintain inside design condition during the periods of maximum outside temperature. The design load is based on inside and outside design condition, and it is air conditioning and refrigeration equipment capacity to maintain satisfactory inside condition. For an example, if you have a room have a heating load more than 2 tonnage, let's for example, and if you place 1 ton AC, it will not cool down the air to desired temperature. Like if we have a temperature of 30 degree inside the room and we just on the AC, but the heating load is more than the capacity of AC, so it cools down the air little bit, like for example 30 to 27, but it not decrease the temperature up to the 23, that is the desired temperature. So we have to estimate accurately how much tonnage of the air condition capacity should be installed that cools down the room on a required time, on a required temperature. So to estimate the heating load, first classify what kind of heating or what kind of load can be produced that needed to be cooled down in the room. So we have two types of heating by its modes of entry into the space and whether it is sensible or latent. There's two types of heat in our normally room. That is a sensible heat. You already learned the sensible heat in the steam tables, when when either water, steam, or solid is heated and its own temperature increase without any phase change, it's called sensible heat. You already learned in the thermodynamics. So gain is added directly to the conditioned space by conduction, convection, and radiation. You already learned in the heat transfer in the thermodynamics. So for an example, direct solar radiations coming inside the room, the PC generates its heating due to the process. We know that PC have a processor which produce heating that is cooled down by the blower, fan, and heat sink that is rejecting in the room. So that is a heating load. Our lights is producing heating load. All of these heating equipment that directly heats the air of the conditioned space is called sensible heat. It is due to the sensible heat. And Another type of heat is latent heat. You already learned the latent heat in thermodynamics. What is latent heat? The phase change process, either latent heat of vaporization. Here we have a detailed definition of latent heat of fusion, heat of vaporization. But now in HVAC we have one kind of just latent heat, that is due to the water vapors are added to the air space, e.g. from vapor emitted by the equipment, occupants and the equipment. Like for equipment we have a hot tea. If for an example, we have to cool down the conditioned space of kitchen. So in the kitchen we have to cook food where the steam is directly added into the conditioned space, and water is added into the conditioned space. Another example, like tea, coffee, it's also evaporating water into the conditioned space, but these are very minimum or very little amount. The major quantity that added into the conditioned space is human sweat, पसीना. जो हमारी the sweat released from our body, it is evaporated into the conditioned space, and that is producing the latent heat. And due to the latent heat, and not by only this person, you can see that in the areas that is very near to the sea, like for Karachi, we have a high relative humidity. So our air already have a very high amount of moisture content that needed to remove from the room, because high humidity also make comfortable effect to the person. Anyway, so this is basically the latent heat. The moisture present in the air is a latent heat that it is needed to remove from the conditioned space. And the sensible heat is directly the temperature of the air. Heat gain through the building, like for the radiation, directly radiation pass through the glass, there is no medium required. And also we have some gaps where the directly hot outside air comes into the room. And also we have a convection, the glass also gets heated, and that's heated glass heat the inside air by the convection. And we have a different mode, all conduction, convection, radiation, all we have learned in the previous slides. Okay, now the sensible heat is due to the heat flowing into the building by conduction through exterior walls, floors, ceilings, door, windows due to the temperature difference on their two sides. The heat received from the solar radiation, which consists of the heat transported directly through the glass of window, ventilators, doors, etc. The heat absorbed by the walls and roof exposed to the solar radiation and later on transferred to the room by conduction. The heat conducted through the interior partition from the room in the same building which are not conditioned. The heat given off lights, example lights, motor, machinery, cooking operation, industrial processes, etc. The heat liberated by the occupants itself means the heat carried by outside air. Yes, in Karachi the outside here have a very high, not sensible heat but latent heat. It's get very high amount of moisture in it. So when the door open, outside air comes in the room, inside the room. So we have a leaks, infiltration here through the cracks in the doors, windows, the frequent opening of the doors, etc. I already given example. The heat given through the walls of duct carrying conditioned air through unconditioned space in the building. So all these are factors that producing sensible heat in the room. Okay. Now latent heat already I just showed a little bit points, but here we have 4 points. The moisture in outside air entering by the infiltration, like opening the when the person entering in the room, so the door will be open, so the outside air infiltrate inside the room that have high moisture content. The condensation of moisture from occupants, I showed you that we all produce sweat, that is pasina. that evaporated in the conditioned space and producing latent heat. The condition of moisture from any process such as cooking foods takes place within the conditioned space. The moisture passing directly into the conditioned space through the permeable walls or partition from outside or from adjoining region where the water vapor pressure is higher. Like if we have a seepage walls, in some areas we have a seepage that has a permeable walls, water is available in the walls, that is also evaporated in the conditioned space. Or if we spill out the water in our floor, it will evaporate, and of course it produces the latent heat gain. And we already learned in the previous slides what affect the moisture to the human body. High moisture means our sweat will not evaporate, and we feel very suffocation. For an example, you come in some congested mosque, masjid, or any space where we have a very high density of persons, so the space eventually becomes suffocated, and that is suffocation due to the high humidity. Okay, so to evaluate the heat produced by sensible heat, we need that following formula. It's a very big formula and have large quantity of factors like outside film surface conductance, inside film, outside area walls, outside area temperature, thickness of all. It's related to the conduction, convection, and the combined effect of radiations. But it is just I'm just showing the formula for your knowledge basis, but we are not going to solve numerical from this long equation. We will solve in mechanical engineering, but you are having a very short course of HVAC. Anyway, we used to have this formula, and nowadays we also not use these formulas. We use directly software to analyze that heat load. Later we will show some slides of a formula how can we estimate heating load through the directly through the software that is being used by mechanical engineers in consultant firms. Heat gained by the conduction through the interior part. This is basically drawings inside the aerial view of the room, where we can see that from the glass and window we get the radiations, but the walls or floor, might be floor, and roofs can be heated through the sunlight on the roof. The sun cannot come directly into the room by radiation, but itself gets heated, and that heated roof heat up the room by conduction and convection combined effect. The roof will gain heat by conduction from outer surface of the roof towards the inner surface of the roof, and then the inner surface of the room heat the room by convection. Okay, solar gain through the outside walls. Yes, we have outside walls and roofs, and we have a formula for solar temperature. So we can directly calculate the heat radiation due to the outside surface air, and we have a very large amount of formula for evaluating it. Anyway, these formulas are used by the software, and the software calculating the heat load. Heat gain from the occupants already discussed. You can see that this is the conference room where the large gathering is sitting, so it is also producing latent heat due to the body temperature of a person. Like body temperature is 37, but the comfortable temperature we required is 23 to 25, 26. So from the person we have a sensible heat, as well as the person is sweating. Due to the sweating, the sweat evaporate in the air and producing the latent heat. And heat gain from the light, equipment, etc. And we have a basic formula to calculate the total load. The total wattage of the light used factor, allowance factor, if we know that use factor and allowance factor, we can directly calculate the heat load from the bulbs, energy saver, LEDs, etc. Now we just come towards the most important part, psychrometric chart. We already discussed in previous slides, but in previous slide we just discuss about the basic terms and terminologies used in the psychrometric chart. But now we are going to solve the numerical by the help of psychrometric chart, and this will be the last numericals. Right now I just showed some just revised some basic terms in it. This is basically a psychrometric chart. Here in the x-axis we have a dry bulb temperature. In the slant line we have a wet bulb temperature like 10 sorry, this is 10, 15, 20, and I already explained what is dry bulb and wet bulb temperature. Some more terminologies. These slant lines having a wet bulb temperature have a humidity of 100%, and after that we have a 90, 80, 70, 60 and so on. Okay, and what about these lines? These straight line is enthalpy line. Yes, enthalpy, that we already learned in thermodynamics. Enthalpy, that as a unit of kilojoules per kg. So all these lines shows this enthalpy, and by the enthalpy we can calculate the heat load, and the heat load is directly proportional to cooling. To reduce that heating load to the desirable temperature, effective cooling should be needed. Okay, and the most important part is specific humidity or absolute humidity in some terminologies, that is gram of water by gram of dry air. That I already explained in live session. You can also watch that video, but again I am revising this terminology. This is the percentage of humidity, relative humidity, showing the amount how much percentage of air can be evaporated in this particular point. Let's suppose we have a relative humidity 50%. So 50% means the air can absorb 50% amount of water that is already present in the air. Okay, and the specific humidity is basically the amount of water divided by the amount of air, dry air without any water. So it is direct the ratio of weight, but relative humidity is basically the percentage. It is a ratio of the maximum capacity of water can be absorbed divided by the actual quantity of water. Okay, so in the relative humidity, both numerator and denominator having a quantity of water, so that's why the unit of relative humidity is in the percentage phase. The gram of water divided by the gram of water cancel out and we get the percentage. But in the sensible heat we have two different unit, the gram of water divided by gram of dry air. Okay, so now comes towards some animation that shows how can we get the required temperature in psychrometric chart. Like if you see that if you select any point, like for example I just select we have a dry bulb temperature 35 and wet bulb temperature for example 20. So if we analyze what are current room condition, we just make the straight line parallel to 20 temperature, just like this, and the vertical line to the sensible heat, also dry bulb temperature. So we get the our desired point. This is our current condition of room. Okay, this is our current condition of the room. But what is basically comfortable zone of the air? We already know that the comfortable zone is is around 65 to 40% of relative humidity and 23 degrees centigrade of a dry bulb temperature. So if we need to go into the our comfortable zone requirement, it will be in the here. This is the 23 degree centigrade, and this is the 50% relative humidity. This is point. This is the actual we have a target of a comfortable zone, but it may be range from 60% of relative humidity to 35 to 40% relative humidity, and the temperature range of, could be 23 to 26. This might be the range of the comfortable zone. So wherever you are, if you are here, if you are here, we need to shift towards the comfortable zone. And in the psychometric chart, if we cool down the air, our circle standard of air goes like this, and due to this portion, you can see that water content in the air will be constant, but after getting the dew point, the water is removing and it expels from the air. So now it's 31 minute. We will cover the numerical in our next lecture. We studied again the process of humidification, dehumidification, and also do one numerical related to the psychometric chart and estimation of heat load. But you can see that from the psychometric chart, by going left, the humidity will not decrease, but after reaching the 100% relative humidity, the water expel out from the air, and then the circle, the point of the air, it goes down like in the vertical direction. If we are going in the vertical direction, the humidity, actual humidity present in the air, it is decreasing. Okay, it is decreasing. So dehumidification, whenever we goes towards downside like this, after reaching the dew point, the humidity or the water present in the air is actually removing. You can see the practical form in our indoor unit. You can see the water is coming from indoor unit. Where the water comes, if you just place the chill water in the glass, you can experience the outside of the glass becomes wet. So the cold temperature, the low temperature, condense the water available in the room. Okay, so this is basically the dehumidification process. And if we goes toward the right side of this chart, it means that we are increasing the temperature, so it is a heating process. Going left side, it is a cooling process. Going downside, it is a dehumidification process, and moving upside, it is a humidification process or gaining heat. If our point is reaching vertically, means there should be any steam in the air that is increasing the water content. So the water previous present in the air is around 0.01, then it shift to 0.025. So upside means humidification, downside means upside humidification, downside is dehumidification, right side heating, left side cooling. So basically these are the processes that can be done in our condition space, and we will discuss the numerical in the next lecture.